setting up hypothesis test. What can sample statistics tell us about corresponding sample parameters? So that's sort of the goal of hypothesis testing. Example, 75 out of 100 patients are cured by a new drug. How confident can we be that over 60% of the population of millions of patients would be cured? So 60% may represent the proportion that were cured by the old drug, and the new drug, at least in the sample, 75 out of 100 were cured. That's 75%. So it looks like the new drug is better, but that could have happened by chance. So we want to know how likely it would happen by chance that 75 out of 100 patients were cured by the new drug if the new drug were no better than the old drug. Okay, so the 75 out of 100, that's our sample proportion. That's p hat. So the p hat is 75 over 100. That's our sample proportion. Or as a decimal, it's 0.75. And that's our estimate for our unknown population proportion. Typically, the population proportion will be unknown. So the p hat, a sample proportion p hat, the estimate for the unknown population proportion. If you go on to Math 251, you'll also have hypothesis tests for some other statistics. We're going to be focusing on the proportions, but the sample mean x bar is an estimate for the unknown population mean mu. The sample standard deviation s is an estimate for the unknown sample standard deviation sigma. The sample correlation coefficient r, estimate for the population coefficient rho. So typically the population parameters are represented by Greek letters. So the population mean is mu, standard deviation sigma. This population proportion could be the letter p, which is a regular English letter, or it could be the Greek letter theta for the population proportion, and then the correlation coefficient is rho. It looks a little bit like a p, but a little bit more rounded than a p. It's the Greek letter rho. Okay, so this week is mainly about terminology. I will work through this one example because it's kind of hard to make meaning out of the terminology if you don't have a concrete example with which to understand it. But this first week is mainly concerned about the terminology. The formal way of asking this question is we're testing H naught, H0 or H naught, P equal 0.6. The new drug is not better than the old. The 0.6 was the cure rate of the old drug, versus the alternative hypothesis HA, P is greater than 0.6. The new drug is better than the old. So in most texts, the H naught has an equal sign in it. Some texts, they'll have a greater than or equal to or less than or equal to sign in them, but it always includes an equal as part of it. The greater than equal sign includes equal. The alternative hypothesis is either going to have a less than, a greater than, or a not equal to symbol. Before testing the hypotheses, it's common to establish the desired level of confidence. That's often 95%. And for this example, we'll use 95%. That's the most commonly used level of confidence. That means our level of doubt is going to be 5%. So 100% minus 95% is 5%, or 0.05. That's the official term for the level of doubt is the level of significance. But I think I like the term level of doubt better than the level of significance. But it's officially called the level of significance. I think the level of doubt more is a better descriptor of what it actually represents. P0 is the proportion that we're using for comparison. In this case, it's the cure rate of the old drug. That's our P0. N is our sample size. In this case, it's 100. Okay, so the exact probabilities are a little bit involve quite a bit of computation. So most of the time we're going to be using the z-table to give estimates for the probabilities. And we can do that if n times p0 is at least 10 and n times 1 minus p0 is at least 10. So if those are if it meets those conditions, we can use the z-table. So we want to check in this case n times p0, 100 times 0.6 is 60. Is that bigger than or equal to 10? And that's a yes. N times 1 minus p0, 1 minus 0.6 is 0.4. 100 times 0.4 is 40. Is that bigger than or equal to 10? And that's a yes. So that means we can use the shortcut rule. So we're going to compute the p-value with this formula here. So it's a probability that of z being less than p0 minus p hat times square root of n over square root of p0 times 1 minus p0. So if we plug in the numbers, p0 is 0.6. P hat is 0.75. N was 100. By square root. P0 is 0.6 again. 1 minus P0, 1 minus 0.6 is 0.4. Okay, so you first want to do what's inside parentheses first. We're finding the order of operations here. So you want to push 0.6 minus 0.75 and then push equals, because we want to do what's inside parentheses first. So after you put that in, you push equals, and then we can do times second square root 100 equals, and then divide by second square root 0.6 times 0.4 equals. And it's approximately 3.06. So it's I get negative 3.061862.178. Okay, and if we round it off, it's approximately negative 3.06. So then we can go to the z-table and look in row negative 3.0 and column 6 in the z-table. So it's negative 3.0, column 6, right here, 0.0011. 0.0011. So that's our p-value. The z-score of 3.06 is called the test statistic. In this formula here, because we have a left-tailed table, and we're doing a right-tailed test, I reverse the p0 and the p hat. But if you're just computing the test statistic, you want to put the p hat first, p hat minus p0, and then the test statistic would be a positive 3.06. So sometimes the test statistic is reported separately. Usually a test statistic of over 3 or less than negative 3 is going to provide fairly strong evidence against H0. Okay, so anyway, our p-value 0.0011 is less than our desired level of doubt, which was 0.05. So we reject H0 with 95% confidence and conclude that the new drug is better than the old. strictly speaking, we never accept H naught. Either we reject H naught or we don't know. Because especially if you have a small sample, it might be that a larger sample would give you bigger evidence against an H naught. So you'll sometimes see in textbooks and even in web assign, you'll see language about accepting H naught, but that technically you should not use that language. The reason some people use that language of accepting H naught is that the double negative is kind of awkward. Like if we fail to reject H naught, it has a double negative, and that is kind of awkward language. So a lot of times people will say they're accepting H naught, but really it's failing to reject. Okay, so some parts of the p-value formulas are sometimes reported separately. The sample statistic is p hat, the null value p0, the null standard error, that's square root of p0 times 1 minus p0 over n. That was these were all sort of included in the formula for the p-value, but sometimes they're reported separately. The test statistic it can be written in this form here, the p hat minus p0 times square root n over square root p0 times 1 minus p0, or you can write it in this form here, where you bring this n down to the bottom, p hat minus p0 times the square root of this whole fraction here, p0, 1 minus p0 over n. This bottom piece of the fraction is actually the null standard error. So we have the sample statistic minus the null value divided by the null standard error. And for this problem, if they want you to report the null standard error separately, square root of p0 times 1 minus p0 over n, square root of 0.6 times 0.4 over 100, 0.0489 something, approximately 0.05. If you recall the empirical rule for bell-shaped data, 95% of the data is within 2 standard deviations of the mean. So this is one standard deviation of 0.05. So 0.6 minus 0.5 minus 0.5, or minus 0.05 minus 0.05 is 0.5, and 0.6 plus 0.05 plus 0.05 is 0.7. So that means if H naught is true, 95% of the time, the sample statistic would be between 0.5 and 0.7. So if H naught is true, then a sample statistic of 0.75 would be unusual. Okay. This page here, I'm discussing the types of errors. Sometimes some of the questions WebAssign have questions about possible types of errors that might happen. So this tree sort of lists the possibilities. Either H naught is true or HA is true, and either we don't reject H naught or we reject H naught. So if H naught is true and we don't reject H naught, then that's a correct conclusion. The probability of that happening is 1 minus alpha, which usually alpha is 0.05, so it's usually going to be about 0.95 probability we don't reject H naught if H naught is true. If we reject H naught and H naught is true, then that's called a type 1 error. Its probability is alpha, which is usually going to be 0.05. And it's decided by the researcher what their level of doubt they want to use, but it's usually 0.05. The other type of error that can happen is called a type 2 error. If HA is true and we don't reject H naught, that's probability is beta. Usually we don't know beta. You have to make some assumptions in order to calculate beta. If you take what 251, actually you may be asked to calculate beta under certain conditions. And then 1 minus beta is called the power of the test. That's if we reject H naught and HA is true. That would be a correct conclusion. Okay. So exercise is it possible we made a type 1 error in example 1? It is, and the answer is yes, it is possible. Our p-value is 0.0011, so that's our probability of a type 1 error. So the p-value corresponds to is our actual level of doubt. Alpha is our maximum desired level of doubt. The p-value is the actual level of doubt, and which is the actual probability of type 1 error. So our p-value is 0.0011, which indicates 0.11% risk of a type 1 error. Is it possible we made a type 2 error in example 1? And the answer is no, because we rejected H0. With the type 2 error can only happen if you don't reject H0 and HA is true. But we rejected H0, so the only type of error that we could have possibly made would be a type 1 error, and we had a 0.11% chance of making that. If example 1 alpha was 0.001 instead of 0.05, what type of error might we have made? Well, our p-value is 0.0011, so if alpha is going to be 0.001, our p-value is more than the maximum desired level of doubt, so that means we would fail to reject H0. So that's possible. So if we don't reject H0, then we're possibly making a type 2 error there. We don't reject H0 and HA is true. Okay, so this one here, just some practice setting up hypotheses. A teacher thinks that students avoid the number 0. To test this theory, the teacher asks students to pick a number between 0 and 9 inclusive and records the results. Let P represent the proportion in the entire student population that would predict the number 0. So there's 10 numbers between 0 and 9 inclusive. So if students are not avoiding the number 0, then they would have a 1 out of 10 chance of picking the number 0. So P0 should be 1 over 10 or 0.1. So then our hypotheses would be H0, P equal 0.1. Students don't avoid number 0. That's the same probability as any other number. Versus HA, P is less than 0.1. That means the students are avoiding the number 0. There's less than 10% chance that they'll pick the number 0. Another example, setting up hypotheses. It is known that 20% of the total adult population is divorced. It is suspected that Viet vets have a higher divorce rate. Okay, so H0, if Viet vets don't have a higher divorce rate, then their divorce rate should be 0.2. That should agree with the rest of the population. So P0 is going to be 0.2. And HA, if Viet vets do have a higher divorce rate, then that means that P is greater than 0.2. So that was just some practice in setting up hypotheses. And that concludes this presentation.